So the last speaker of this session is Robert Cardona, who will talk about the topology of Bott integrable fluids.
Okay, so, well, let me first thank the organizers because I'm really enjoying this conference. It's amazing how well it's done for being online. And, well, I'm probably one of those speakers that there's at least one in each conference where I am kind of at the boundary of the topic, which is Poisson geometry. But still, there are some connections with it, as you will see as we go on. So, well, I'm a student of Eva Miranda, and my thesis deals with somehow combining two worlds, which is the analysis of steady Euler flows, which is some equations that model the fluid dynamics somehow, and using symplectic and contact geometry and topology techniques to say things about it. So what I will be speaking about is some kind of solutions to the Euler equations, which are called, well, I am calling them Bott integrable. And this is what I will be speaking about. Firstly, I will introduce the topic and Arnolds theorem, which is a really important theorem that will be very important for this work. Then I will explain two different results, one about realizing some integrable fluids, and another one about finding topological obstructions to the existence of such solutions. And I will not be technical at all. I will introduce almost anything that it's needed because I know that probably not a lot of people is familiarized with what I will be talking about. So, well, of course, what I need to first state is Euler equations, which, as I said, model the dynamics of what's called an ideal fluid, which means that it doesn't have viscosity, which is in the case for Navier-Stokes equations, and it's incompressible. And even though they are originally formulated in the Euclidean space, as everything in mathematics, you can actually formulate it for any arbitrary Riemannian manifold of any dimension, even though I will be speaking of the three-dimensional case. And, well, these are the equations, where x is basically the velocity of the fluid, and p is a scalar function, and is the pressure, it's called the pressure. And all the differential operators, of course, are taken with respect to the metric that I fixed initially. And here's a photo of Euler. This is something Eva does a lot, and I like it, which is putting photos about the famous people you talk about. What I will be mainly focusing on is the analysis of steady solution. That means that I'm forgetting this t dependence. Can you see my pointer when I move it? Okay, so I will be forgetting about the time dependence. And why I'm focusing in these solutions, and this is because it becomes very geometric, actually, and surprisingly somehow. And you can actually look for another formulation of the equations, which is equivalent, but much more nice for people working in differential geometry. And to do so, you introduce the one form alpha, which is the one form dual to x by the metric, and a function which depends on the pressure and on the metric, which is called the Bernoulli function, which I'll be denoting B. And then the equations for steady solutions are actually equivalent to this set of equations, where the first one is just telling you that the contraction of your velocity field with d alpha is exact for some function B, which is the Bernoulli function. And the second equation is just telling you that your vector field is volume preserving. It preserves the Riemannian volume, of course, the volume induced by the metric. Okay, this is what I was telling. And something that needs to, well, that one can already obtain easily from the first equation is that actually this Bernoulli function is an integral of the vector field in the usual sense, so that the vector field is tangent to the level sets of B. And of course, this implies that the solutions can have very different behavior depending on this function. Okay. Another concept that is very important in this context is the vorticity vector field, which actually can be associated to any vector field, but let me say it's for an Euler flow. And this is defined as the only vector field satisfying this equation, which is telling you that when you contract it with the volume, you obtain the alpha. Okay, and why do you care about this vector field? Well, actually, because this vector field commutes with x in the Lie sense, let's say, not Poisson. And it is whenever you are at a point which is regular for your Bernoulli function, it is independent from x. Okay, so that basically this leads to some dichotomy somehow of behavior, which is that if b was constant, for instance, then your vorticity is always parallel to x because it's nowhere independent. And then this is what it's called a Beltrami field. Okay, it's a vector field which is parallel to its vorticity. And this kind of, well, they are, of course, a particular case of solutions to the Euler equations. And they are very well studied somehow, and they can be used to prove that a lot of different topological properties can happen in steady solutions. And the other case, which is the contrary, would be if B is generic. And by generic, I mean that the critical level sets are of zero measure, let's say. For instance, if B is analytic, if B is Morse-Bott, then what happens is that almost everywhere, X commutes with another vector field, which is the vorticity. And this dichotomy is captured by a very well-known theorem, which is called Arnolds structure theorem. And this theorem basically inaugurated this field of topological hydrodynamics. And this theorem is telling you what happens when B is analytic or in fact, generic in this sense I was telling you. So if I denote by C the union of critical level sets, which will be somehow the Bott set, the fluid has a very rigid behavior. So that basically, once you take out this Bott set, your manifold is trivially fibered by invariant tori. So it looks somehow like an integrable system in symplectic geometry. Okay, and this is what it's written in here. And you can even say more that the flow is conjugated to a linear flow in each torus. Okay. As I was telling you, even though this theorem is stated with an analytic function, which is non-constant, this is very important because if it was constant, then we would have a Bernoulli function. And if the Bernoulli function was smooth instead of analytic, then you need some additional assumption, like you have a zero measure critical set, or your Bernoulli function is Morse-Bott, then you can say the same thing. One question that arises from here, and that actually I found in a course given by Daniel Peralta Salas, which is a collaborator, is that, well, if there is a solution in this hypothesis, something that is automatically implied is that there is an analytic function, all whose regular level sets are tori, because from the theorem it follows that this invariant tori are the level sets of the Bernoulli function, which is an integral of the vector field. And one can ask or wonder if this is a topological abstraction, in the sense that does every three manifold admit such a function? And actually we will address not exactly this question, but we will, inspired by this question, we will address it in the last part of this talk. So something else that can be said about this theorem is that it's an a posteriori consequence. So it's telling you if you have a solution with such properties, then blah, blah, blah. It has some rigid behavior and it looks like an integral system. But actually, there's not a lot of examples in the literature about examples of flows that are in this hypothesis. Something that doesn't happen in the Beltrami case, where you have, for example, every three manifold admits a Beltrami field for some metric. This is something that a priori it's not known in the analytic, well, in the, let's say, non-constant case of a Bernoulli function. So this will be somehow the domains that I was telling you of trivial fibered tori. If the manifold was allowed to have boundary, then you can have trivial fibrations by cylinders instead of tori, of course, when it touches the boundary. Okay, what I will be, in this first part of the work, I will be assuming something else, which is that the vector field, the velocity field of the fluid is non-vanishing, okay? Something that a priori could not be true, okay? So when I come here to the equations, whenever I mean at a critical point of the Bernoulli function, x could be vanishing. And this I'm avoiding, okay? I'm telling you x is always non-vanishing, okay? And I will take the hypothesis of Arnold's theorem, which is that B is either analytic or Morse-Bott. I will be very interested in the Morse-Bott case, which is the easiest one somehow. And let me call this an Arnold fluid just because I will be using a lot this kind of solutions. And a theorem, which is somehow partially proven in different points of the literature, is that if you have a three-manifold and a non-vanishing vector field which has a Morse-Bott integral or an analytic integral, it is necessarily what's called a graph manifold. And the graph manifold, for those who are not familiarized with three-dimensional topology, it's just manifolds that are constructed by gluing Seyfert manifolds with boundary, okay? And for those who don't know what's a Seyfert manifold, it's just manifolds that can be foliated by circles. This, of course, doesn't cover all the three manifolds, okay? In fact, only a few of them, but some of the very well-known as you might expect. As I was telling you, there's only a few examples of fluids in the hypothesis of Arnold's theorem, and this includes the sphere and the torus with the round and the flat metric in a paper of Kessing-Cooksin and Peralta-Salas. So the goal of this work, the first goal, is to try to check if every graph manifold admits such a solution, at least for some metric. And this is what one can prove using the classification of Seyfert manifolds, which is already quite old. And you can show that any graph manifold admits such a fluid. Arnold fluid means non-vanishing solution with an analytic Morse-Bott function, okay? Then is when the symplectic geometry comes into play to help improve this theorem into a much stronger version, which comes by using the methods of theorem number 1 with the theory of Fomenko and his collaborators about isoenergy level sets of Bott integrable systems. That's the theory, for instance, covered in this famous book of Bolsinov and Fomenko that pretty much everyone that works in integrable systems probably took a look at some point. So what you can say by combining this theory with methods developed in Theorem 1 is that actually given any Morse-Bott function admissible, which means that can possibly be the integral of a non-vanishing vector field, there is an Arnold fluid such that the Bernoulli function is exactly this Morse-Bott function. Okay, so that the realization theorem is full somehow, it's complete. A corollary, of course, of this theory of Fomenko is that the invariants they develop give a topological classification of these fluids. And by topological classification, I mean a collection of invariants that tells me what's the ambient space and how the foliation by level sets looks like, okay? Lastly, something that's quite cute, but actually doesn't work for all flows, is that these constructions that we do in Theorem 1 and 2 can be symplectized to obtain literally Bott integrable systems for some symplectic structure, okay? Symplectize, I mean, by taking your three manifold times minus epsilon, epsilon, like in the usual sense for contact manifolds. But this can only be done somehow ad hoc, like for these constructions. Like you can find Arnold fluids that are not, at least in my sense, cannot be symplectized, okay? The fact that there are Bott integrable systems of any topological type is a theorem originally due to Fomenko and his collaborators in 1989. So let me now explain. I will sketch the proof of Theorem 1, okay? And, okay, so a key lemma is that actually you don't need to construct the metric and you only need to be worrying about a one form. And this is because of this lemma, which, well, it's introduced at several points in the literature, but for instance, it was used in this context of Euler flows in a paper by Reichmann, Torres de Lizaur, and Peralta-Salas, is that given a non-vanishing vector field which preserves some volume, if I find one form which is positive on it, then you can find a metric such that this form is the dual to X. And furthermore, I can impose that mu is the volume form, the Riemannian volume form, okay? So what follows from this is that if given a graph manifold, I can find a volume-preserving vector field in a one form that satisfies the first Euler equation for some function b, which is Morse-Bott or analytic, then we are done, because I can apply this lemma and I can find the metric, and then X solves the Euler equations for that metric. Okay. So what you do is, using the classification of Seyfert manifolds, you break it into different blocks. Actually, the blocks one is a trivial S1 bundle over a surface with boundary. And then at each boundary component, you attach either the unique cotangent bundle of the Möbius band or some solid torus via the twist. Okay. This, if you have learned a little bit about Seyfert manifolds, is classical. Then at each block, you construct an Arnolds fluid. But then, of course, they don't necessarily glue together to give a globally defined thing. And this is where you need to introduce an interpolation lemma, which tells you that at the gluing locus, in a neighborhood, you need to interpolate between both Euler flows in a way, in a controlled way, that the Bernoulli function is still Morse-Bott, for instance. Okay. So to keep a picture of what's happening, is that, okay, you start with an S1 bundle over a surface with boundary, in this case with genus 2, and then you attach two solid tori here via some den coefficients, which is telling you how to glue them, and the unique cotangent bundle of the Möbius one, okay, via somehow a trivial identification of frames. And then you construct some fluids in each of these blocks, and at this gluing locus, which are neighborhoods diffeomorphic to a thick torus, you interpolate between both solutions, okay? And this is containing this lemma that I won't be commenting, but just for you to know that this is somehow the key point. That is that you can interpolate in a way that you can control the critical points of the Bernoulli function. This is this last part, okay? You are not adding any critical point, basically. Finally, once you are finished with this, you have an Arnolds fluid in every Seyfert manifold. So to obtain it in every graph manifold, you just need to adapt a little bit your interpolation lemma so that you can glue Seyfert manifolds with boundary between them. Okay. With this, you can obtain an Arnolds fluid with a Morse-Bott Bernoulli function. And to conclude about the analyticity of the Bernoulli function, you need to use a theory of Sciotta, developed by Sciotta, who tells you in which circumstances a function is actually analytic in some charts. Okay, and so you can conclude Theorem 1, which was telling you that every possible manifold admits an Arnolds fluid with an analytic Bernoulli function. So as I was telling you, if you want to realize any Morse-Bott function as a Bernoulli function, you need to combine this with the theory of integrable systems, and this I will be speaking about in the parallel session. So if you like integrable systems and you don't know anything or very little about this theory of Fomenko, you might be interested in the parallel session. Let me finish with some final discussion, which is related to the question I was asking in the introduction, which is, are they obstructions to the existence of Bott integrable fluids? And okay, we know that if X was non-vanishing, then it has to be a graph manifold. And now we know everything about the graph case somehow. But now I can drop this assumption and I come back to the general case, which is simply a vector field satisfying the steady Euler equations for some metric, which is no longer non-vanishing a priori. Then this theorem that was telling you that it's a graph manifold no longer applies, because it really uses that X is non-vanishing, okay? This theorem that was partly proven, this theorem here, which is telling you that it has to be a graph manifold, only applies if your solution had no stagnation points. It's non-vanishing, okay? So now we don't know anymore this. So a priori, the manifold could be of non-graph type, okay? This is because the topology of your function changes. Now you can have, for instance, critical points, not only critical circles, and because you can have stagnation points, okay? We can call this, if you want, singular Arnolds fluid, and you can ask if there exist in non-graph manifolds. Again, if you're familiarized with three-dimensional topology, a non-graph manifold you can look at it as a, well, of course, it's not of graph type, and furthermore, or equivalently, it has some hyperbolic component in its decomposition of Thurston geometrization. Okay. And what you can prove is that if it's not of graph type, your manifold, and it satisfies some, let's say, assumption, which is that it does not admit an embedded projective plane, then there is no steady solution to the Euler equations with a Morse-Bott-Bernoulli function. And this is true for any metric. So we are speaking about really a topological abstraction. Okay. And this is, of course, is the first example of a topological abstraction to the existence of some solutions of some kind, somehow. And so this partially answers the question we were asking. But actually, what's curious is that the question was if there is a function which has all regular level sets which order I, and this is not what I'm claiming. So here I'm using the steady Euler equation much strongly than just to say that the regular level set order I, okay? But still answers what the motivation of the question, which was, when can you say that there are no solutions, okay? And as I was telling you, for instance, this class of manifolds, even though there is this extra assumption that there is no embedded projective plane, this includes all hyperbolic manifolds, for instance, which are known to be pretty much all of them, okay? In some sense. The proof of this is a little bit more somehow intricate. It's not so easy to explain, but I will keep it for the parallel session because it's still quite geometric. It's, I don't know, I like it. And about the hypothesis, the fact that it does not admit an embedded projective plane can probably be dropped, but I need it for the proof I'm using. But I think it's a simplifying assumption. It's probably avoidable. And the fact that it's a Morse-Bott-Bernoulli function is also needed. This doesn't work in the analytic case. I mean, in the analytic case, it's not known if you can find a solution for a non-graph manifold. And I think it's probably not true that they exist, but the proof I use doesn't work. You need the Morse-Bott assumption. And then let me just give you some references because, because you're probably not familiarized with some of these topics. So the Arnolds theorem was proved in this first paper. This is the translation to French. Then there is this classical book about this whole topological hydrodynamics thing by Arnold and Kessin. And here there's another little course by Daniel Peralta Salas where I found this question about the abstractions, topological abstractions. And then, well, if you want to know more about this whole approach about combining contact and symplectic geometry with steady Euler flows, this first is the work I was speaking about today. And then some other two works that we have done with collaborators also in this philosophy of using contact topology. Like here is more contact topology, and this first that I was speaking about is symplectic topology. And that's all. So thanks a lot for your attention.
Thank you very much, Robert. Let's all give a round of applause to Robert, including emojis, emoji applause, everyone.